Hey everyone, this is Mohammed Nadeem and welcome to my YouTube channel. Today in this lecture, we will discuss about the solenoid. Solenoid is such like shape. When we arrange the conductor in this like shape, it will form the solenoid. And if we attach this side of the conductor with the positive terminal of the battery and this side of the conductor with the negative terminal of the battery, then the current will start flowing in this conductor. So the direction of the current is given by this. So here these arrows represent the direction of the currents, the direction of the conventional current. Okay, so here is the direction of the conventional current in the conductor. As we know that if the current is flowing in the conductor, it will produce the magnetic field around itself. So here this conductor will produce the magnetic field around itself, and that magnetic field will be arranged in such a way that that magnetic field will be added up inside this solenoid. Okay, due to which the parallel magnetic field lines will be formed inside this solenoid, and the one side of this solenoid will be the south and the other side of this solenoid will be the north. And the magnetic field lines will also present around this solenoid, but we ignore that here. Why? Because the ideal solenoid is those solenoid which have the strong magnetic field inside and the weak magnetic field outside. And for the ideal solenoid, the magnetic field will be in the inside this solenoid will be parallel. So here is the arrangement of the magnetic field lines. So here is the arrangement of magnetic field lines that are arranged inside this solenoid parallel to each other, and the strength of the magnetic field will be more inside this the solenoid, and the strength of magnetic field around this solenoid will be negligible. And for the ideal solenoid, the magnetic field around this solenoid will be 0. So here this is the ideal solenoid because the length of this solenoid is greater than the radius of this solenoid. In this cross is used for inside in this conductor, and here the current is moving outside. Okay, so similarly here the current is moving on this side towards you, and here the current is moving from you towards the screen. So we denote that the current is towards you in the form of dotted. So these circles are actually the conductors. So here these are large number of conductors. So this is actually the vertical the cross-sectional diagram of this solenoid. So in order to find the magnetic field, we will consider the Amperian loop here. So I'm going to consider this red loop is actually called the Amperian loop. So here it means that we select the Amperian loop inside this solenoid. So here this is the Amperian loop. And if we see here, there is a large number of conductors present inside this Amperian loop, and each conductor is represented here by these circles, and the current in this conductor is moving towards you away from the screen. Okay, therefore we consider that in the form of dotted. And now we will apply the Ampere law, and we will find the magnetic field around this solenoid. Is A, and this is the B, this is the C, and this is the D. So here is the length of this Amperian loop is this, and this is actually the other length, and this is actually the other length, and this is actually the other length. So this is called the Amperian loop, and here from this length we know that the expression for the Amperian loop is given by the summation of B dot del L is equal to mu naught time of the I enclosed. So here we have four sides of the Amperian loop. So this equation for that can be written as B dot del L1 plus B dot del L2 plus B dot del L3 plus B dot del L4 is equal to mu naught time of I. This is the expression of the Ampere's law. So here this is actually the L1, this side, and this side is actually the L2, and this side L3, and this side is the L4. Now here B dot del L1 is actually the dot product, so this is become B del L cos of theta, and this become B del L. So this is del L1, this is become del L2 cos of theta plus B del L3 cos of theta plus B. So for this B del L 4 cos of theta, which is equal to mu naught time of I. So the angle between the B, the magnetic induction, and del L1 is so here this is del L1, and this is del L2, this is del L3, and this is del L4. So this side of the Amperian loop is actually present in the magnetic field here. So this internal side of the Amperian loop is present inside the magnetic field. So the direction of the length here is from the bottom to the top. So here this is the direction of the length. The direction of the length of the internal side of the Amperian loop is parallel with the direction of magnetic field. So here this side, this side of the Amperian loop is parallel with the external magnetic field. So here the angle for this del L1, so here the angle for the B, between the B, the magnetic induction, and del L1. So here this is the B, magnetic induction, and this del L1, the angle between B and del L1 is 0. So we can write here B del L1 and cos of 0. Okay. And now for the B, the magnetic induction, and del L2, the angle will be here. So from the diagram, the direction of the Amperian loop, this side of the Amperian loop is this. So from the right towards the left is the direction of the Amperian loop. This the del L2 part of the Amperian loop, and here the direction of the magnetic field is perpendicular to this side of the Amperian loop. So here the angle between the B and del L2 is 90. So I'm going to write that here the B del L2, this is B del L2 cos of 90 for this side of the Amperian loop. Now for this side of the Amperian loop, so here for this side, this external side, so here we for this external loop, the direction of the this side, the del L3 is from the top to bottom, and here internally the direction of the the magnetic field is actually from the bottom to top. Okay, so here the angle between this B and del L is 180. because one is from the top to bottom and the external magnetic field from the bottom to top. So here for the del L3, the angle between the magnetic induction and del L3 is 180. And similarly, for B, the angle between the magnetic induction and del L4. So here we have del L4. So this side of the Amperian loop, the lower side of the Amperian loop is actually the direction of the length is from left to right, and internally the direction of the uh, magnetic field is from the bottom to top. So here in this case, the direction of the direction of this del L4 direction is this, and the direction of external magnetic field, sorry, and the direction of external magnetic field is from the bottom to top. So here the direction of external the direction of magnetic field is from the bottom to the top. So here is the angle is 90. So for this the angle between the magnetic induction and del L4 is given by this magnetic induction and del L4 cos of 90 is equal to mu naught time of I enclosed. So we know that the cos 0 is equal to 1. So this become the B del L1, and instead of cos 0 we will put 1 and plus B del L2 instead of cos 90. Cos 90 is equal to 0. Okay, plus this cos 180 is equal to minus 1. So this become what we can say, this become minus B del L3, and this is again cos 90, and cos 90 is equal to 0. So this become B del L4 into 0, which is equal to mu naught time of I. So this equation implies that here this B and del L1, and this becomes 0 plus 0, and this is now minus B del L3, and this become again 0 here, and which is equal to mu naught time of I. And we know that for the ideal solenoid, so as I discussed before that for the ideal solenoid, the magnetic field is stronger inside the solenoid, which is parallel to each other, and the magnetic induction, the magnetic field outside of this ideal solenoid will be 0. So here the outside of the solenoid, the part of the Amperian loop is this. So here this is del L3 and B. So in this side, through this part of the loop, the magnetic field will be 0. So here I'm going to put the B here 0. So if we put B is equal to 0, so this become this is actually B del L1. Okay, this is for this side. So B del L1 plus this 0 minus, instead of this B we will put 0, because for the ideal solenoid the magnetic field from this part of the Amperian loop will be 0, because for the ideal solenoid the magnetic field outside of the solenoid will be 0. So the magnetic field on this part of the solenoid will be 0. So here the magnetic field, if I put 0 here and these are 0, so in the left side of this equation, only B del L1 will be present, and on the right side of this equation, it will become equal to mu naught time of the I. This equation become B and it's instead of del L1, I will put L, okay, and which is equal to mu naught time of I, okay. Here B is equal to here B is equal to mu naught time of I divided by L, okay, mu naught time of I divided by L. So we will proceed this equation here. Here the equation is B is equal to mu naught time of I divided by L. And for n number of the coils, here we will put n. So it become equals to n mu naught I divided by L. So the number of turns per unit length. So number of the turns per unit length is equal to this small n. So instead of this n by L, I will put this small n. So this equation now become B is equal to, instead of this n by L, I will put this small n, and here mu naught, and this is I. For finding the direction of magnetic field, so put your right hand around this coil. The curl finger of your right hand, the curl fingers of your right hand will be pointing in the direction of the current, the conventional current, and the thumb of your hand will represent the direction of the north side of the magnet.